My name is Dr. Esther Trufan, and in this video, we're going to explore the various ways in which we can represent organic molecules. By definition, organic molecules are chemical compounds that contain at least one carbon connected to hydrogen, so they also contain hydrogen, and they may, but this is not necessary, it's an optional category, they may contain other elements such as oxygen, nitrogen, sulfur, phosphorus, and others. When writing the molecular formula of an organic compound, we always start with carbon. Then we follow it up with hydrogen, and any other element in addition to these is going to come next in order of the alphabet. So if we have nitrogen and oxygen, nitrogen comes first, oxygen next. If we have oxygen and sulfur, oxygen goes first, sulfur goes second. The most common organic compounds that you may find in your general chemistry laboratory are glucose, which has the molecular formula carbon 6, hydrogen 12, oxygen 6, and citric acid, which has the formula carbon 6, hydrogen 8, oxygen 7. Now, this formula only tells us what kind of atoms and how many of each there are in our compound, but it doesn't say anything about how they are connected to each other. The formula of glucose could be shared for 30 or 40 different compounds, and the same goes for the citric acid. Another way to represent an organic compound is using the structural formula. This tells us how the atoms are connected. Not how those bonds are oriented, but how they are connected. So if a carbon is connected to an oxygen, is that a single bond or a double bond, etc. Here we have the structural formula of glucose. And we see that each carbon has an OH group associated with it, except the very last one, which has a double bond to the last oxygen. Here we have the structural formula for citric acid, and here we see that each carbon has connections to hydrogen, except the second one. And then we have these carboxylic acid groups, which involve carbon connected to an oxygen through a double bond, and carbon connected to an OH group through a single bond. The condensed structural formula is more commonly used in organic chemistry, and this summarizes the connectivity of our atoms. Some of the things are omitted for simplicity, like is a bond single bond or double bond. But it does indicate if we have repeating units or branching groups by putting them in parentheses next to the carbon to which they are attached. So for glucose, we could write its condensed structural formula like this. We have a carbon, and this is the last carbon, which has one hydrogen and one oxygen attached to it. So we can derive that that oxygen is doubly bound. Then we have 4 repeating units where a carbon has one hydrogen and one OH group associated with it. And then our final carbon has 2 hydrogens and one hydroxyl group. For citric acid, this has that branching OH and then that branching carboxylic acid group. So we start with the first carbon that has 2 hydrogens and a carboxylic acid group. Then we go to the second carbon. This one has the OH group, the carboxylic acid group. And then we have the third carbon in the chain that has only the carboxylic acid group attached. The formula that gives us the most information about how the atoms are connected is the skeletal formula. This one is simplified in its representation because it omits the carbons and it omits the hydrogens. There are some assumptions that are made here. So if we look at the skeletal formula of carbon, every time there is a kink in the chain, that is where we have a carbon. And here we have a total of 6 carbons. The hydrogens are not included either, because the assumption is carbon will always have 4 bonds. And if we have 2 bonds already taken up, one by this hydroxyl group and one by the rest of the chain, then this carbon will also have 2 hydrogens attached to it to satisfy its 4 valences. Applies to all the others. When we look at the citric acid, we find that there are 6 kinks. 1, 2, 3, 4, 5, and 6 kinks. That means 6 carbons. And in every place where carbon does not have 4 bonds around it, we need to add enough hydrogens to get it to 4. So let's see how we can interconvert between the different type of formulas that are available. This exercise is very useful if we're new to representing organic molecules and a first Google search yields mostly a skeletal formula from which we may need to derive other formulas. Here is diallyl disulfide. This is the precursor to the smell of garlic. And if we have this original structure, we should be able to derive the other formulas. For the condensed structural formula, it is important that first we start by understanding the skeletal formula. So here we have 3 carbons on one side and 3 carbons on the other. If our carbon at the end has a double bond to the next carbon, then that means it has 2 bonds available for connection with the hydrogen. So we can add 2 hydrogens. When we look at the second carbon, this one has a double bond and a single bond, leaving it available for 1 more addition. So that will have 1 hydrogen. The next carbon, carbon number 3 here, has 2 bonds, 1 to the carbon and 1 to the sulfur. So that means it can have 2 hydrogens. On the other side, it's exactly the same thing. The first one has 2 bonds. So it has 2 hydrogens. The second carbon on the right side will have 3 bonds already, giving it 1 hydrogen. And then the final carbon has a double bond, so it will have 2 hydrogens. This simple process already gave us our structural formula. So with the carbons in place and the hydrogens included, we already have our structural formula. For the condensed formula, we can start with our structural formula and put it together. We have a CH2 group that was first, and that is followed by a CH group that is followed by a CH2 group. Then we have a sulfur, another sulfur. Then we move to the right side of the sulfurs and we have a CH2, another CH, and at the very end we have a CH2. The molecular formula involves counting the number of carbons, the total number of hydrogens, and the total number of sulfur atoms here. So we have carbon 6, hydrogen 10, sulfur 2. We can try this again with something a little bit more complicated. Geraniol is one of the scent ingredients in roses, and this one looks a little bit more complicated than the other one. However, it also has 2 double bonds except no sulfur, which means less smelly. Every time there is a kink in the chain or an ending to the line, we have to write in a carbon. And so to interpret our skeletal structure, we place in our 10 carbons. Next, on every carbon, we need to get to 4 bonds. If it doesn't have 4 bonds yet, we need to add enough hydrogens to get it to 4. So this terminal or ending carbon will have 3 hydrogens. This one will also have 3 hydrogens. This carbon that has the 2 CH3 groups attached to it and is doubly bound to another carbon already has 4 bonds around it, so it does not need any hydrogens. Next, we have a carbon doubly bound to another and singly bound to another. This carbon will have 1 hydrogen to get to 4. Our next carbon has 2 single bonds, so it will take on 2 hydrogens. Then we have a carbon with 2 bonds to other carbons. This one will have 2 hydrogens attached. Next is a carbon with 2 single bonds and a double bond around it. So it already has 4 bonds. We don't add any hydrogen to that one. But it has a carbon attached to it, which is only a single bond. So that carbon will need to take on 3 hydrogens. Next in the chain is our carbon with a double bond and a single bond on it. This will gain a hydrogen. And next is our carbon that has 2 single bonds, 1 to a carbon and 1 to an OH group. This one will need to take on 2 more hydrogens to get to 4 bonds. Now we converted our skeletal structure into a structural formula. To move from this to our condensed structural formula, we can do it a couple different ways. I will show you the one that treats these CH3 groups as a group and then uses the rest of the chain as the foundation for our formula. We start with CH3. We have 2 of these, and both of those are attached to a carbon that doesn't have any hydrogens on it. After that carbon, we have a CH. Then we have a CH2 group. That's this one. Then we have another CH2 group, followed by a carbon. And that carbon has a CH3 group attached to it, but not the following carbon. So that goes separate, and we put it in parentheses next to that carbon. Following that is a CH group, which is this one. Following that, we have a CH2 group, and then finally we end with an OH. To convert this into a molecular formula, once again, we count the number of carbons, hydrogens, and oxygens, and we find that we have 10 carbons, 18 hydrogens, and 1 oxygen, making carbon 10, hydrogen 18, oxygen 1, which is implied by not having a subscript as our molecular formula.